So welcome to the last of the lectures in this seminar on conformal field theory. Today we're going to put together all the evidence that we've been assembling over the past 9 lectures or so and write down a Hilbert space corresponding to a conformal field theory. So a Hilbert space, what is it? Well, it's a vector space with an inner product and some kind of inner product, and there's a topology induced by this inner product, and the Hilbert space is complete with respect to that topology. That's what a Hilbert space is, and the question is, how do we attach such a space a Hilbert space to a conformal field theory? What are the states? What should they correspond to? What are the observables? What should they correspond to? How does the symmetries, in particular the conformal group symmetries, how do they act on this Hilbert space, presumably as some kind of unitary? So that's the goal for today, to build a Hilbert space that we can attach to a conformal field theory, and that way of attaching the Hilbert space matches aspects of what we would call conformal symmetry, or it allows us to represent things that we would call conformal symmetry. Now, there's a kind of standard way to attach a Hilbert space to any kind of field theory via so-called Whiteman functionals. So this is, roughly speaking, what we're actually going to do in this lecture today. You can use Whiteman functions to build a Hilbert space for any sufficiently well-behaved quantum field theory. And what that amounts to, when I say those words, is that you take the data that a good quantum field theory gives you, namely the endpoint correlation functions, and then you use the endpoint correlation functions to build a vector space and inner product on that vector space. And you work quite hard, and then you find out that it's a Hilbert space. That's essentially what we're going to do today. The difficulty is we don't know, why don't we just do this for our favorite quantum field theory? The problem is we don't generally know the endpoint functions very well. So maybe I'll say make a bit more commentary on this, because this is why conformal field theories in 1+1 dimensions sort of are sufficiently nice. They allow us to carry out this program in a sense. So these Whiteman functionals, they're none other than just endpoint correlation functions. And we use these to build an inner product space. We essentially define kets So we define kets like this, just by sticking fields in front of the vacuum, and we get an inner product. Once you've got some kets, you might want the inner product. And then how might we find it? Well, if this field operator is sort of Hermitian and under sufficiently nice circumstances, you could just go ahead and define it like so. So this is in the very specific case where this field operator is Hermitian. Now, okay, that's fine. You could do that. I mean, there's some technicalities, right? It might be that you have some zero norm vectors here when you do this, that you take the inner product and then you get the number 0, right? It might be, right, that for some reason the correlation functions do that, but that's a common sort of feature when you're building a Hilbert space, and you can just mod out by these zero norm states. And then you have to argue that indeed these kets are like not poorly behaved distribution type things, but real legitimate members of a Hilbert space. That's actually harder because they really are distribution type valued objects as written here, right? I've got the field operator at the space-time position x1. And so there's no solution to this. The only solution is to smear out your field operators. So this is still, should be understood as metaphorical. Like what I'm saying here is not mathematically rigorous, but this is the ideas behind the construction. So what you really do is you define inner products between vectors I denote like this, which are, I'll call this Wn, x1, xn, y1 up to ym, which are just smeared out versions of this. It's the only difference. So it turns out, okay, these things are not well behaved enough to be elements of a Hilbert space in general. But when you smear them out by sufficiently nice functions f and g are smearing functions, then you can construct things that look like respectable members of a Hilbert space and build an inner product on it, and that's how you get a Hilbert space corresponding to a sufficiently well-behaved quantum field theory. So this is all fine and good, and yeah, you could go do that for your favorite quantum field theory. The difficulty is that for this program to work, you have to be able to compute these correlation functions here. Now, in your favorite quantum field theory, if it's Gaussian, no problems, right? We have Wick's theorem, we can go ahead and do that, and you can work relatively hard, and this will be fine. For other quantum field theories which have interactions, you might hope that perturbation theory might allow you to get this program to work. Some cases, yes. Some cases, yes. Actually, the only way we have in general to argue that these correlation functions are sufficiently well behaved is literally the path integral. You can make the path integral formulation rigorous in certain circumstances by going to imaginary time and Wick rotations and so on. And that's how progress has been made traditionally in this area, is via the path integral. It's kind of ironic that this thing which is regarded as not mathematically rigorous is more or less the only way we have to make this Hilbert space work out. Or you could be so lucky that you have a theory where you can work out all the endpoint functions. And we have one. It's called a conformal field theory. So here we have a mechanism to actually control all these endpoint functions, or n plus endpoint functions. And that's, roughly speaking, what's going on behind what I'm going to tell you today. Although the way we implement it in conformal field theory it looks a bit sort of obfuscated, but this is what's going on. So let's get to it. So our first piece of notation is to just denote the vacuum of our CFT as 0. This is the interacting vacuum. This is not a perturbative statement. This is the vacuum. And we're going to, our first step is to associate states with operators and vice versa. So to every operator, we're going to associate a state. And morally, actually, this construction is equivalent to how we associate states and operators in, say, quantum information theory. So suppose we have some Hilbert space, which is like some finite dimensional Hilbert space, C to the D. Then, and we have some operators, or some operator acting on this Hilbert space, so that's a D by D matrix. And there's a well-known device to building a quantum state associated with this operator. What we do is we have to double our Hilbert space. As follows. And we choose a very special state. We construct the following state, phi plus, and we associate with the operator A the following state A, defined none other as A tensor the identity acting on this state here. So this is how we associate states with operators in quantum information theory. You have some operators, you have some initial Hilbert space, you build a maximally entangled state of two copies of the system, and you associate to the operator A the state A ket, defined by acting on half of this maximally entangled state with the operator A. Here's a little diagram for this. Time is running from left to right. So that's a standard device we exploit in quantum information theory quite often to get a correspondence between states and operators. Now we're going to exploit a device morally very similar to this. Morally very, very similar actually. Now, if you have a field operator, that's a operator which acts at some point in space-time. Notice we're using complex coordinates now for our space-time. Then you can associate to any field operator an in and an out scattering state. You just run time backwards or run time forwards and have A act on the vacuum. Now this limit doesn't exist in the ordinary sense of a limit, it exists in the sense of scattering theory. It's just about the same. Some 0, sigma 1, say. And this sigma coordinates, that's the cylinder coordinates, and I guess I'll just draw a picture to remind you of this coordinate system. So sigma naught is the time coordinate in the usual quantization quantum system on a circle, and you run time backwards on this field operator from some fiducial time. And that, presuming that this limit exists in some sense, will give you a state that does no longer depend on time. Depends on space, but not time. Now, if we change coordinates to z coordinates instead, we'll actually see that it doesn't depend on space either, because we've compactified our space-time. And so all points at infinity are the same point. And so we end up with this definition here. So corresponding to every field operator, there's an in state defined as, just take your field operator and send it off to infinity, infinitely far in the past. And because there's only one infinity, when you compactify the complex plane, we're doing things on the Riemann sphere, there's only one state that comes out of this. And we'll call that A in. So that's one state that we can associate with an operator A. Actually, another state we can associate with an operator A, namely the out state. And we'll make a choice that will seem a little peculiar to begin with, but it'll turn out to be very natural. We're going to associate an out state to A, but not as a state, but as a bra. So we have a way, there's a way to go to plus and minus infinity on the complex plane. Suppose you're at minus infinity, then one way to transform minus infinity to plus infinity is to do the conformal transformation, w equals 1 on z. That sends you off to the other infinity. So the two infinities in the complex plane. So the infinity of minus sigma naught equals minus infinity is the origin, right, under this conformal mapping. And the infinity of sigma naught equals infinity is the other one, way off. And so one way to get at that point in terms of our complex coordinates is to first transform z equals 1 on z, and then send z to 0. Right? It's the same as sending w to this infinity. And that there's a conformal transformation, and so that's why I've drawn this tilde here. This tilde here means we've done that conformal transformation, but we haven't. But we want to express everything in terms of z. And when you do a conformal transformation of a field operator, then it transforms in a funny way under this conformal transformation. So there's all these factors, right? And we'll actually chase down these factors in the case of a primary field. In the case of a general field, it's not so easy. So for a primary field, a hat z bar equals phi hat z bar, we know how primary fields behave under conformal transformations. So that's the rule for how a conformal field transforms under a conformal transformation of the argument. So at least in that case, we're going to be able to work out the out state corresponding to a primary field. So we'll do it now. Use that notation, phi out. So in states are easy, but out states require a bit more work. Or out bras. I should say sort of more maps to under F. So we apply immediately this conformal transformation here, w equals 1 on z. We use this rule for primary fields, and we pick up some factors. For having done this transformation. And we're going to look at this and we're going to say, well, whatever, this is a funny thing. Now, if this funny thing were an operator, and this was, if this funny thing were an operator acting to the left, then we might think of it as the adjoint of an operator acting to the right. So we're going to use it to define, it's not actually going to call it, it's not proving that this is the adjoint, we're going to use it to define an adjoint on this thing. So this defines the following operation, which we'll call adjoint. And this in turn we'll use to define the adjoint of the, yep?
Sorry, but I think there's something not clear in your notation. You say that H tilde is the transformation operator, or the transform operator under F, but you say that, of course, but you say that phi tilde maps to a transform operator.
So under a conformal transformation,
you say the transform operator F tilde transforms to something else.
Ah, okay, yeah. Right. So
I think you
I have to get rid of, yeah, you're right. I have to get rid of the tilde, don't I? Yeah, I think that's the quickest way to fix that. Yes. Yeah, under a conformal transformation, a primary field goes like this. And a tilde here is not yet transformed. And so I have to replace it with that transformed version. That's what the notation's meant to do. It's not quite doing it as it was. Okay, thanks. So now we've taken this definition here and used it to define the adjoint of field operators. In going from this line to this line. Notice that the bar has moved. So instead of the argument here being z bar, we've defined the adjoint of this operator here to be, sorry, we define the adjoint of this operator here to be the result of putting in 1 over z in the first argument, 1 over z bar here, and so on. That's the definition of this adjoint operation. And so we have to be a little bit careful about that bar. So you'll notice that it plays an important role later on. And then once we've done that, we can define this line here and set z bar and z to 0. So even though the arguments of the first entry here is now z bar, since we're sending z bar to 0, that will be the same as if the argument was z and that was z bar. And that's why that equals phi in dagger. It's an important subtlety. And if you use these definitions here, you can see that you get a nice inner product that is finite. It doesn't diverge. So we can start putting in all the variables. Yep.
Shouldn't the bar on
No, it shouldn't be. No, we've got it, so the bar is here. This is perfectly fine because phi in is the result of sending z and z bar to 0. And so that's the same whether or not we send z bar in that argument to 0 or z bar putting it in that argument to 0. It's the same answer. It's the same answer whether we put in 0 there and then there, or there and then there. So it's a useful device. However, because we want to get these complex conjugates on different things, because we have a formula for this correlation function. Way back when we looked at 2-point correlation functions in conformal field theory, we had an expression for that. It's like 1 over xi to the 2h, 1 over xi bar to the 2, 1 over xi to the 2h bar, 1 over xi bar to the 2h. Or other way around. Duh. This thing, the expression for this here is exactly right to turn these into absolute value signs. And so this becomes independent. So we have a little recipe that we've cooked up that will allow us to define things that look like kets in some vector space, vectors in some vector space. We have a duality pairing and we have an inner product. And it's independent of the space-time location of the fields involved because we send the fields off to plus or minus infinity respectively. Now morally, this is just here, the vacuum is playing the role of this maximally entangled state that we introduced to build a state operator correspondence in quantum information theory. This is some bipartite entangled state between some system and some copy of the system. So the vacuum is a state extended over all of space-time. In particular, we think of the vacuum as sort of like pertaining to degrees of freedom infinitely far in the future and infinitely far in the past. So you can think of the degrees of freedom infinitely far in the past as being somehow independent of the degrees of freedom infinitely far in the future. So you can think of the vacuum as being kind of like a bipartite quantum state. And all we're saying here is that A in is sort of like just taking your operator A hat and acting it on 1/2 of the maximally entangled state. So the vacuum isn't maximally entangled maximally entangled in conformal field theory, but it's very strongly entangled. So you can make some hay from this analogy here. And A out, if you cared to define it as a ket, would more look like probably complex conjugate, which we didn't do, but you could think of it that way. So you think of the vacuum of conformal field theory as kind of like an entangled state between degrees of freedom infinitely far in the past and infinitely far in the future. It's not a bad analogy, but you can get a long way with that. Now once you've got these things, phis, you can start building more vectors, right? Once you've got a couple of vectors in a Hilbert space, you can get lots more by acting on them with your favorite operators. And that's how we're going to build our Hilbert space. And in fact, we're going to build our Hilbert space by acting on one of these in or out states with the moments of the energy momentum tensor, or otherwise known as the Virasoro algebra. So we have a whole bunch of things that we know how they should act already at our disposal. And the way we're going to build a Hilbert space is we're going to take the vacuum or one of these in or out, in states, sorry, and act on it with Virasoro algebra operators, these L0s, L-1s, and L1s, and just keep acting on it, and keep acting and building many, many, many more vectors until we get enough vectors that we can take the linear combinations of all of them and we can call it a Hilbert space. So that'll be the strategy. The strategy turns out to work quite nicely. Give very sort of precise Hilbert spaces that we'd like to attach to conformal field theory. So the first step in this procedure is to first convince ourselves that the vacuum is invariant under a subalgebra of these transformations. So the subalgebra generated by L0, L-1, and L1, that closes when you work out all the commutators. You always get that the commutators of these things are linear combinations of L0, L-1, and L1. So these generators correspond to global conformal transformations. So remember that energy momentum tensor is the generator of space-time deformations, and these three particular moments are the global conformal transformations in infinitesimal form. Now, we can ensure that that's the case. We can ensure that, that the vacuum is invariant. I mean, the very least that a conformal field theory should have is that its vacuum state is invariant under conformal transformations. This is like the global one, sorry. And we can ensure that by demanding that the corresponding in states are well defined. So the in states, in particular, of the energy momentum tensor. So that's pretty much the bare minimum you would require from the energy momentum tensor, namely that if you apply it to the vacuum and you send z off to minus infinity, that things don't explode. That is regular. Seems reasonable, right? And you can see that that condition there actually contains this condition here. So the way to argue this is you just use the definition of the energy momentum tensor in terms of the L's. So if you recall from the previous lecture, Tz defines L hat of n's. The L hat of n's are just linear combinations of the t's with some coefficients. And if you demand that as z and z bar go to 0, that this doesn't explode, well, that's the same as saying that these vectors, Ln hat times naught, have to vanish for all n greater than -1. Otherwise it'd blow up, right? And similarly, so we got a lot more than just SL2C invariance, right? We've got that the ground state is annihilated not only by L minus 1, L naught, and L1. So firstly, a corollary is that L minus 1 all annihilate the ground state, which means in particular that if you exponentiate these generators to find the action of a global conformal transformation, it leaves zero invariance. So the ground state is indeed invariant under global conformal transformations. That just comes from demanding that these in and in states here are well defined. But we also gain more conditions, namely that L hat n 0 equals 0 for all n bigger than -1. And now I'm going to show that using the OPE, we can see that primary fields, these in states, are actually eigenstates of the Hamiltonian for our system. So if you recall, the Hamiltonian of a conformal field theory is L naught plus L naught bar. And I'm going to argue now that these primary field operators, phi z, they actually build eigenstates of this combination L naught plus L naught bar. And in particular, the in states will land you in different sectors of the Hamiltonian, different energy eigenvector or eigensectors of the Hamiltonian. And it all boils down to the following identity. Which we can work out using this OPE. So if you know how LNs commute with primary field operators, then you might be able to prove this statement that primary fields create eigenstates of the Hamiltonian. And the way you might be able to prove it is, well, you just apply phi to the vacuum, apply an Ln to it, commute it past, and then hope that it's an eigenstate, right? That's the general strategy. Well, let's see if that strategy has any hope of working. So the first step is just to express the Ln's back in terms of the energy momentum tensor. That's just the definition. And to use that nice trick about commutators and contour integrals. So if you remember from last lecture, the commutator of two operators can be expressed as a contour integral around some closed circle, which includes and excludes the point W. And then at this moment here, if you look at this, we have the combination of the energy momentum tensor and a primary field. So this is the moment to use the OPE. Right? The OPE tells us how these two things behave as Z goes to W. Oh, sorry, I already used that commutator trick. This is a contour integral, a tight contour integral around the point W. It's a little circle around W. So just here, there's a contour C. The contour C, well, if you have the point W in the complex plane, then the contour C is just a tight little circle around the point W. And we take the limit as epsilon tends to 0. So the commutator can be expressed like this contour integral here. Since we're only evaluating the fields when they're very close to each other, we need only look at their singular behavior. And the OPE for a primary field with a stress energy tensor is defined essentially to be this. It's the only thing that's consistent with the correlation functions. And so we have two singular terms and a third term which is regular. There's an infinite number of terms here, but when you do the contour integral of any regular function, you just get 0. So this, you only have two terms emerging. And thus we end up with this result here. So we have a way to evaluate the commutator between one of these L's and these phi hats. And we're going to use this is really a useful formula to ladder between eigenvectors of the Hamiltonian. So let's do exactly that. So we're going to define an asymptotic in-state corresponding to our primary fields. So primary fields are really labeled by h and h bar, their dimensions. And that's why instead of using this notation, I'll just switch over to calling the state h and h bar. So if we use this equation star, we can see that when we apply L hat naught to this h bar, that we get h bar. This comes from star. So it's probably worth pausing a moment to derive this result. So L naught hat acts on phi naught naught bar. So then we want to put a commutator there. And we can do that because L naught acts on the vacuum as 0, it annihilates the vacuum. And then we use star. And we set W to 0. And it's very important that we have a 0 up here, otherwise things wouldn't work out. So W goes to 0. So in this equation here, n is 0. When we use star here, n is 0. So W to the n is the number 1, which is why when we said W to 0, we don't get 0 for this first term. W to the 1, well, that goes to 0. This term straight out vanishes. So we're left with the number 1 here, multiplied by phi hat 0, 0 bar, h1. So indeed, it gives us this formula here. And there's a similar formula for L0 bar applied to this. I'll squeeze it in here. It's the obvious one. We just take bars of everything. And so we see that this state, this asymptotic in-state h bar defined here, is an eigenstate of our Hamiltonian. It has to be. We apply L0 plus L0 bar to it, and we get h plus h bar, which is, if you like, twice the real part of h. So it's an eigenstate. But we actually get so much more. So this equation star is really very, very powerful. It tells us that these Ln operators, they act like ladder operators. So the L minus n's, they act like creation operators, and Ln's act like annihilation operators. Before discussing that, I'll just point out a simple consequence of this commutation relation. As long as n is bigger than 0, these are actually 0. The ln's applied to these states here. So we can get a whole bunch more states by taking modes of our primary field and applying them to the ground state. So just like we did for the energy momentum tensor, we can express any primary field as in terms of a Lorentz series or a Fourier series, depending on what language you prefer. In doing so, we can define the modes of a primary field just by this Fourier relation, this Fourier type relation, say, on the unit circle. And inverting that Lorentz series, we can express the modes, well, in terms of the primary field.
Excuse me?
Yep.
I think there has to be a bar
Oh, there has to be a bar. Thank you. Yeah. Gosh. So we can just invert this series here to find what the modes are in terms of our original field operator. And then our definition of the Hermitian conjugate, that peculiar definition we introduced, is implemented on the real surface where z equals z bar via the definition phi dagger mn goes to phi minus m. And also, there's just like we used for the stress energy tensor, in order that the in and out states are actually well defined at all, we need that these modes annihilate the ground state, at least for m bigger than minus h and n bigger than minus h bar. Now at this point, we could do everything with z's and z bars, but it's a bit tedious. And it turns out you can always reconstruct the dependence on z bar if you know the dependence on z. So we're going to drop dependence on z bar because everything separates. So if you look at these expressions at the top of the board, you can see that the dependence on z bar separates from the dependence on z. It's just separate integrals. And so we write everything just in terms of z, and we understand that to mean that as that there is Z bar dependence, but you have to put it back in. Just basically by copying everything and multiplying by Z bar, putting a bar on it. So we're going to just write our field operators depending on Z now. There we go. So our original field operator, which depends on Z and Z bar, we'll just write only half of it like this. But whenever we get to our final expressions, we know that there is also Z bar dependence. We have to put it back in. We'll also define the holomorphic modes. In a similar way. So putting this together with the help of this equation star, can work out the commutator of one of these modes here with a Virasoro generator Ln equals this expression here, n times h minus 1 minus m times phi n plus m. And it's this behavior here which shows us that these phi m's are kind of like raising operators or lowering operators. So these phi minus m's, they increase the conformal dimension by m. So we could look at the Hilbert spaces formed by applying all these modes to the vacuum, and that would give us a highly intricate set of vectors with inner products. Instead, we're just going to focus now on states that we can construct just by applying LNs to some in state, some primary field in state. So that's going to be the last thing that we'll do. And that will allow us to build a subspace of the total Hilbert space of this conformal field theory. So the topic of the study, or the study of the representations of the Virasoro algebra that you get by applying primary fields and Virasoro generators to a vacuum state, is a highly intricate topic. It fills many, many chapters and often whole books, the combinatorial structures that come out. So certainly won't have time to cover that. I'll just show you the basics, the basic subspaces that you get just by applying these Virasoro generators Ln just to say the vacuum, or some other in state. Sort of worth just looking at the Virasoro algebra, we see that this L minus M operator has a raising operator type quality as well. Okay, so now what we're going to do is we're going to build a subspace of our Hilbert space which is invariant under the conformal group and invariant under local conformal transformations. It's going to be a closed subspace by itself that will give us a unitary or projective unitary representation of the conformal symmetries. It won't be the whole Hilbert space of the theory, it'll just be a little subsector. And the way you build it, well, you start with your favorite in state, and then you start applying L minus M's to this state here, and that constructs things called descendants. Now you could choose phi is the identity, right? That's a perfectly valid in state, it's called the vacuum. So we also get, everything I say will extend just to the sector found by deforming the vacuum by space-time deformations. So in terms of this asymptotic in state, we can define descendant states. These are all, this is an eigenstate of our Hamiltonian here. The vacuum's an eigenstate of the Hamiltonian. This is an eigenstate of the Hamiltonian. And corresponding to any of these very special eigenstates, we get a whole infinite tower of other states, which you get by applying just the symmetries to the state. So these are starting with some in state, say the vacuum or some other state where we've applied the primary field, we can get an infinite sequence of other states by just applying L minus K's for K's in increasing order like that. Now we can just choose by convention that the K's are in increasing order, because if they weren't, we could just use the commutation relations to move these LKs around until they are in increasing order. So this descendant state there, that is an energy eigenvector for our Hamiltonian, just by using the commutation relations. And the eigenvalue is just H plus, well, all these K's. These K's are all integers. So if our initial state was, say, the vacuum, then the eigenvalue of this new state found by applying all these L's to it is just the sum of the K's. The sum of the K's is an integer called the level. So if you now find, you just keep applying these L's, there's an infinite number of L's to apply, keep applying them, you can build more and more descendant vectors like this. Zillions and zillions of descendant vectors, an infinite tower of descendant vectors. That gives you a subspace of the full Hilbert space. This is not the full Hilbert space, this subset here, this subspace of states. It's not because, well, we could have applied a different primary field here. But this subspace has a very important property, namely that if you apply any Virasoro generator operator to a vector in the subspace, you stay in that subspace. So it's invariant under the Virasoro algebra. And such things are called modules. It's just the name in maths that we give to them. You can think of them as representations. And there's a name we give to these modules found by applying L's to asymptotic instates. They're called Verma modules. A lot of very intricate combinatorics to do with Verma modules. Definitely worth chasing up if you're interested. So this little sub-representation just found by saying, taking one primary field, building the asymptotic in-state, then applying all the Virasoro generators, that means just all the local conformal transformations to that state, to build the smallest Hilbert space which is closed under the action of Virasoro. That's this Verma module. So there's a whole study of Verma modules and their properties. Let's talk a little bit more about the interplay between H, the scaling dimension, and C, the central charge. So it turns out we can derive very, very many interesting constraints on the value of H and C. So we can derive, it turns out not all values of C and H are possible. We can derive many, many constraints on these values just by using now these algebraic relations that we already have at hand. So the Virasoro algebra, just for completeness. Oops, n plus m. So that's just using these algebraic relations, we can already learn about the interplay of H and C. So here we've learned something quite important. So we can compute this combination here, L dagger minus n, L minus n. Apply the Virasoro algebra to this term here. Well, first we take the adjoint, apply the Virasoro, and then we get this expression here. Now, as n becomes very large, so this thing here is positive, right? As n becomes very, very large, this becomes negative if c is negative. So we already learned that c must be greater than or equal to 0 if this is a positive inner product. The other option is that the inner product of h with itself is 0. That's the other option. So just looking at this thing here, knowing that it's a positive quantity and letting n tend to infinity, so it's positive because this is equal to the inner product between two descendant states. Sending n to infinity, we see that c has to be strictly greater than 0, otherwise this would become negative for some value of n. Furthermore, you can, if n is 1, this implies that h is bigger than 0. So if you just choose n as 1, so n1 cubed minus 1 is 0, so 2n times h times that has to be positive. So as n tends to infinity, well, that forces h to be positive. And the final simple observation is, what if h is 0? Well, if h is 0, then this is in fact the vacuum. And that follows from just applying L0, L minus 1, and L1 to the h is 0. So any primary field with h is 0 is the vacuum. All right, and then I think we have one final comment that's very interesting, worth mentioning. And that is, what about C is naught? Can we have interesting Verma modules for C is naught? Let's have a look. Well, I guess you can already start to work this out just looking at the equation on the board there. C is naught implies for the case H is naught, so the vacuum, that the inner product of H with itself is 0. So that's trivial, right? So you can't get interesting representations of the conformal group and the local conformal transformations for C is naught. You really need, it's required that C is strictly greater than naught. Now that's just for H is naught. It also, you might think, okay, well, maybe we don't get interesting unitary representations of the local conformal transformations for C is naught. But what about H is not equal to naught? Maybe you just go to there and you can get interesting representations. Well, actually it turns out not either. So for arbitrary H, what you do is you look at the gram matrix of two of these descendant fields, these descendant states, namely L to the minus 2n of H and L to the minus n of H. And that gram matrix, which is just the matrix of the inner products of these two particular descendant states, well, it has determinant. So the determinant of this gram matrix, which is just the product of its two eigenvalues. If you go through and work it out, happens to have this determinant here. I don't expect this to be at all obvious, but that's what it is. And that goes negative for n is large. So sort of a pretty non-obvious thing to do. In fact, it was so non-obvious, a 3-page paper was written on exactly this observation. So for n goes to infinity, this gram matrix, it's a 2 by 2 matrix, which is positive, it should be positive, right? The gram matrix, which is just the matrix of inner products, should be a positive matrix, so the products of its eigenvalues should be positive, but the determinant, which is this, goes negative when n goes to infinity. So the only possibility is that the inner products of all these vectors here is 0. So again, you have a trivial representation for C is naught. So the only way to get a unitary or projective unitary representation of local conformal transformations, the only way you can do it is if C is not equal to naught, this central charge. So you might, right at the beginning of this course, we discussed the algebra of local conformal transformations. We saw it was equivalent to this Witt algebra, which is just this commutator there, but with no C term. And we said, okay, maybe we can find unitary representations of just this algebra there. We've now seen that that fails, right? Because when C is naught, all those representations would have to be trivial. So we're forced to deal with projective unitary representations. That's just the language for adding on a term like this, which is a co-cycle, if you know about group cohomology. Well, that's it. This is just the barest of introductions to CFT. We've hardly touched on anything yet. You'll be able to pick up books on CFT, on conformal field theory, and make it to like chapter 4 or 5, based on the stuff that we've briefly touched on in these 10 lectures. But the full intricate beauty of conformal field theories, we've not even gotten close to that. So there has been tremendous amount of work in this area, and we know very, very many things about conformal field theories. We can classify them, we can attach them to microscopic physical systems, and we can even make a large part of conformal field theory rigorous mathematically. And all of this awaits you if you want to build on the foundations that we've laid in these 10 lectures. But for now, that's it for this course. Thank you very much.